Okay, so let's look at the warm-up. Let's talk about solving. Okay, so solving. So when we solve, right, we're doing something very specific. So let's hear what you had to say. What does it mean to solve a polynomial equation? What do you think? Find x, find what x is equal to, in what situation? Tell me more. Yeah.
In a situation where y is equal to 0?
Exactly, which is if y is 0 and you have an x value, what is that point? An x-intercept, right? So, yeah, go ahead.
I said to find the root that makes the equation true.
Absolutely. When you're finding any solution, you're finding a thing that makes it true. In this case, an x that makes it true. In this case, the truth is that it equals 0, right? And you want to find the x that makes that true, right? Okay, so we're trying to find x values that make the equation true, to make y equal to 0. And it also, by benefit, just gives us our x-intercepts, our roots, and our zeros. Now, let's write that down to start. So we're finding x values that make y equal to 0, right? They make that situation true. They make that true. Okay? Now, the other thing it gives us, just by benefit, is we find our zeros slash roots slash x-intercepts if, what am I going to say? Anyone know? No. Is there ever any time where it didn't give us our x-intercepts? Think back to quadratics. We found solutions, but they weren't x-intercepts. They're imaginary. So if real. All right? Okay, so how is this not factoring? Because that's a key area of confusion. Not factoring, right? What's the difference? Anybody know the difference between factoring and solving? What do we say factoring is? Yeah.
Factoring is making an equation as simple as it can become.
Yeah, so it's breaking it down into the multiplication of smaller things. Okay? So you take a thing and you change its form into a more broken down form, but you are not solving when you do that. Okay? So factoring is breaking down. It's not solving. All right. Last piece, and then we'll move on to examples. Let's look at some quick, just little, and you can choose whether to draw these or not. Let's think back to what we remember about solving. So, say I have this parabola here, right? How many solutions does that have? Real solutions? Two. And you know that because there's two x-intercepts. There's 2 times where x has a value and y is 0, right? So remember, we had y equals x squared to get that, and then we turn y into 0, and we find the x, like x squared something, and then we find the x that makes that true, right? We find those values, okay? Now, why do you think we always found, well, typically found 2? Sometimes we found 1, sometimes we found none in terms of real solutions. Why do we typically find 2 in most quadratics? There's something that's a hint there.
Exponent.
The exponent, right? It was x squared. Think about a line, x to the 1. How many x-intercepts can that possibly have? 1. It can only cross once. So let's take that to that understanding and extend it to polynomials. How about this example? What type of function is that? It's cubic. So it would be like y equals x third something. How many solutions do you think that has? 3 real solutions, it looks like, right? How do you think you could predict that? Yeah.
Looking at the degree.
Exactly. The degree equals the number of solutions. Okay? That's a great way to check your work, to make sure you found them all. If you're doing an x to the 4th and you found 3, go back, you might have missed something. Okay? Maybe you lost something along the way, you forgot to bring it down. Okay? But you should get the same amount of solutions as your degree. Now, I just said that, but what about, and this is the final extension before we start going through examples, what if I had that? That's cubic, right? How many solutions does it have?
Yeah, one.
Well, we just said cubic solutions have to have 3 solutions.
Sometimes that's not hard.
What do you think?
Imaginary things.
Yeah, so this must have 1 real solution and 2 imaginary solutions. Yeah, and we're not going to get into imaginary yet, but I wanted you to see where we're going with that, okay? So when we're solving, like algebraically, not with a graph, right? A lot of times we finish and we move on. Just check, do yourself a favor. Did I find 3 for this cubic function? Did I find 4 for this quartic function, right? And sometimes you'll check and you'll find you didn't, and you need to just recheck your work. Okay, so remember, factoring and solving are different, but they're related. We factor in order to solve, right? We need to factor in order to solve, right? So let's talk about factoring first. We'll do another example. All right, so first thing I notice here, right here, x to the 3rd, 2x squared, minus 8x. Well, it's not one of my situations, but I forgot the first thing I checked for is a GCF. Does it have one? Yeah, anytime x goes into everything, that at least that is your GCF. So we're going to pull out the GCF, right? And I get f of x equals x parentheses, and then divide everything by x, right? And I get x squared plus 2x minus 8. Now, when you GCF, you have begun factoring. You've broken it into the multiplication of the smaller things. But you always ask yourself, and you focus in on this, what's left inside, can I keep going? Is there any more I can do? Yes, this is a regular classic quadratic, so we're going to try magic x, right? And I have minus 8 on the top, 2 on the bottom. Multiplying to get a negative, adding to get a positive, must
4 and minus 2.
4 and negative 2, right? So f of x equals x, don't lose that, x plus 4, x minus 2. Okay?
Not supposed to get rid of the x even when you
No, absolutely not. Because remember, when you're factoring, you're breaking down into the multiplication of smaller things, and you want to be able to get back if you needed to. At every step, you should be able to get back. Like, we went from here to here to here. Well, let's look at the middle step. Could I get back to the first step? Yeah, just distribute the x and I'd get back, right? The bottom step, could I get back to the one before that? Yeah, I could just FOIL this to get back, right? And then multiply the x, and then I'd be all the way back, right? So you want to think, can I get back if I needed to? And you don't want to lose anything that would prevent you from getting back, right? Okay, so we have, we've factored, right? We're fully factored, so if the instructions were just to factor, you'd be done, right? But let's move to solving, okay? So this is fully factored, and you always want to get fully factored before you move on. But if we were solving, well, what's the difference here? We made y equal to 0. We're trying to find those x-intercepts. Y is 0 at an x-intercept, right? So now, think about solving, right? You're trying to find the x that makes it true. Okay, so if I never taught you how to factor, our only choice would be to randomly plug in x's and see if when you cube it, multiply it, or square it and multiply it by 2, then minus 8 times it, would I get 0? Right? That's the only way we'd be able to figure this out, right? And it would take a very long time. So we use factoring to break it down into easier pieces to solve, right? That's what factoring is. You're breaking it down into easier pieces to look at, right? You don't have to look at the whole thing at once, okay? And there's a product property that comes into play. We'll see how much we remember about it. So anyway, we already factored this, so we don't have to redo it. Let's just bring this over, right? And because you have to factor first, right? Because it would be really hard to figure this out right now. And I got, it was x times x plus 4, x minus 2 equals 0. Okay? So if you have this situation, think back to your quadratic situation, right? Think back to your quadratic situation. And, I don't know, maybe pretend the x isn't there for now. What would you do to solve this? And why would you do it? That's actually the more important reason.
You would put it down to solve it to equal to 0.
Okay, good. And you were saying x plus 4 equals 0, right? Okay, so this is my first class today that phrased it that way. And just in case anybody's thinking this, I'm going to address it because this is where we run into mistakes. And if it was you, that's fine because it was working. A lot of people just think you flip the signs. So negative 4 and 2, right? But the problem is, that's because these are easy equations, right? What if this was 2x plus 7, right? It wouldn't be as that easy. What if it was an x squared in there? And you'll see that, right? So we have to remember the why this works. Somebody explain the zero product property. Yeah?
Do 0 equal to the number, and then you use so for example, this plus 4, you would equal that to 0, and then you would distribute the 4 to both sides.
Correct. And that is closer to the why. But you're still just explaining this step. Why on earth would I make x plus 4 equal to 0 right now? There's a reason behind it. Yeah?
Zero properties says anything times 0 equals 0.
Correct. So we got to take a step back and think about what we have here. We have something times something times something, and the result is 0, right?
Must have a 0.
So something in there has to be 0. If not, everything in there is 0. We have to account for all of them being 0, right? Because if this times this times this is 0, well, then these things might be 0. So we account for that, and we say, remember that the equal sign, it can also just be the word is, right?
Yeah.
Either that is 0, or that is 0. So I literally write that. I say, well, either x is 0 equals 0, or x plus 4 is 0, or x minus 2 is 0. One, if not all of those things have to be true. And we account for every possibility. Okay, so then I have really easy equations, right? This one's done. This one, minus 4, x equals negative 4. This one is plus 2, x equals 2. Okay, we did it. Now, really important to understand it with the simpler problems, because when we get to the harder ones, you're going to have to be locked in on that zero product property. Okay, before we move on, how many solutions did I find? 3 solutions. Okay, and why does that make sense? Just if we're like sense checking our answer.
Because the highest exponent is x to the 3rd.
Right. In other words, this was a degree 3 function. So I'll give you an example of why checking this works great. A lot of people, when they GCF, they like to just get rid of it. They accidentally say, and you even ask, do I still need this x? Well, if I got rid of this x, how many solutions would I have? 2. I would not have enough, right? That's why we don't get rid of it. We need all our solutions, right? This is a 3-degree function. I need 3 solutions. And there you go. These are also our x-intercepts, right? Okay, cool. Now, we're going to the rest of our situation, or our examples, will be what we did last class with the factoring, and then what that looks like when you take it all the way to solving. Okay? So, let's look at this next example. And I filled in these steps on the side. You can write them in as we go if you want. I'm going to be working on the example over here. It just seemed like they were taking up a lot of time in the last classes, so I just put them over on the side for you. All right, so we have quadratic form. We know that because it goes from 4 to 2 to nothing, right? That's a good sign for us, a little thing to look at to find quadratic form. We know that when we have quadratic form, we do magic x. I have 12 on the top, minus 7 on the bottom. Oops. Which would be minus 4 and minus 3 to make that work, right? And when I start factoring this, I end up with minus 4, minus 3, and then what goes in the front of these? X squared. And then I ask myself, can I keep going? With the 4, it's a difference of perfect squares. So this breaks into more pieces, and I have x minus 2, x plus 2, x squared minus 3 equals 0. Okay? Now, can I keep going with the x squared minus 3? No, which means we're fully factored. If we are fully factored, we are ready for zero product property. Even if it looks a little weird right now, you'll see it works. Okay? Now, after we're fully factored, zero product property would tell us whatever is multiplying gets equal to 0. So these things, there's 3 things multiplying. This x minus 2 equals 0, x plus 2 equals 0, and x squared minus 3 equals 0. 2 of these will be rather easy, like usual, right? Just add 2 to both sides, and I get x equals 2. Or I minus 2 from both sides, and I get x equals negative 2. But what about x squared minus 3? How do I solve for x with x squared minus 3 equals 0? Yeah? Exactly. So this is an isolating the square, right? You have a square and a number. You get the square by itself, square root both sides. Use the solving properties that you know, right? So I would add 3. I'd get x squared equals 3. Then I would square root, and I get x equals plus or minus the square root of 3. And that is that. Actually, let me ask you, how many solutions do I have here? 4, right? Plus or minus, that's 2 solutions. That's a plus, that's a minus. Those are 2 different spots on the graph, right? So I have 4 solutions, and that makes sense, right? Because we had a degree 4 function. Okay, so, another time where sense checking that would help. How many people here have forgotten the plus or minus before? Right? Well, if I did, and then, wait, I only have 3 solutions. Oh, I forgot the plus or minus. Yeah?
Couldn't you also do plus or minus 2?
Yeah, you could. Yeah, you could write this as plus or minus 2 and plus or minus 3, or square root of 3. Okay, moving along. If you didn't get those steps down, we do need to get through these. We only have about 7 minutes. So they're on OneNote. You can get them when you do your homework, okay? Okay, what's the problem here? Well, I don't even, I know I always say look for GCF first, but that's if everything's on one side. Like if everything's not on one side, that's the very first thing we got to do. Because we got to get everything to one side. So, well, I guess you could, right? But I would suggest just moving stuff first, just to keep the order of things. But you could divide by 3 right now. But you do need everything, all the x's on one side. I wouldn't move the bigger one away. I would move the small ones to the big one. You know what I mean? Yeah. So move 18x by subtracting 18x on both sides. And I get 3x to the third minus 18x equals 0. Okay, I do need to check for that GCF. And now I see I have one, right? My GCF is 3x. So I'm going to pull that out. It doesn't go away, or I'll lose a root. And I get x squared minus 6 on the inside. And now I can't continue to factor that, so what do you think I do? Is 6 a perfect square? No, be careful. Okay, so 3x equals 0. X squared minus 6 equals 0. And I solve it. If 3 times the number is 0, what is that number? 0, right? So x equals 0 over here. And then here, I have x squared equals 6, square root, x equals plus or minus the square root of 6. How many solutions did I find? 3, very good, because it was a degree 3 function. Make sense? Yeah. Okay, one more, and then I'll hand out your homework and let you keep copying the steps if you need to. All right, so we've done a GCF, we've done quadratic form. What do you think is going to come up here? Grouping, yeah. Okay, so if I have this situation, 3, 2, 1, nothing, remember, there's a little 1 there, then I will use grouping. But there's also another problem here. What's on the wrong side? The 4. Right? So I minus 4 on each side, so I can get it equal to 0. X to the third plus x squared minus 4x minus 4 equals 0. Okay, now grouping. 3, 2, 1, nothing. Got my group. My GCF in the first case is x squared, which leaves me with x plus 1. Over here I have minus 4, which leaves me with x plus 1. It's good news, right? The x plus 1 is my new GCF. It comes out front, and the rest goes in the back. X squared minus 4 equals 0. Okay, so am I ready? Yep. Anybody notice anything? Difference of perfect squares, right? So I get x plus 1, x minus 2, x plus 2 equals 0. And then break it apart. Zero product property tells me x plus 1 equals 0, x minus 2 equals 0, x plus 2 equals 0. And each of these problems is pretty easy to solve. X equals negative 1, x equals 2, x equals negative 2, and I had 3 solutions for a degree 3 function, so I feel good. Okay? Now, again, remember, if you like writing down steps, I purposely chose to focus on concept over steps, but I'm providing them. They're on the OneNote. You can write them down. Okay? Let me give you your homework, and then we're good to go. It's mixed practice, right? So you can't use the same strategy for each situation. That's why I was saying having the graphic organizer helps, and I would recommend having it out while you work, because the very first thing you need to do is identify which situation you have. Otherwise, you won't know what strategy to use, right? And then sometimes the situation doesn't even reveal itself until a step or two into it, right? Because the first thing we want to look for is what? Yeah, GCF. And then a lot of times when you find that GCF, you pull it out, suddenly you look with fresh eyes at a new problem, and now you see, oh, it's sum of cubes. Oh, it's quadratic form. But you didn't see it before the GCF was pulled out, right? So always look for the GCF first, because you never want to try to attack it with a GCF in there. You want to make your life easier. And then after that, pretend it's a new problem. Pretend that you are looking at it with fresh eyes. Now what would I do? Now which situation am I in? Okay? There won't always be a GCF, right? But sometimes there will be, and you won't be able to crack the problem until you pull it out. Okay? So with that being said, which problems would we like to see?
7.
All right, so 7. All right, so again, like I said, first thing you want to do is say, do I have a GCF? And then you notice you don't, right? This doesn't have a number, this doesn't have an X, there's no way that they all have something in common. So the next thing you want to do is just figure out which of our situations it is, all right? When I look for what situation it is, it's helpful to look at the exponents, right? Because I have 4, 2, nothing. 4, 2, nothing, right, is always one type of problem. What type is that?
The one where you do the magic X. And then
Yeah,
you get
it's quadratic form, right? So if I look at that 4, 2, no exponent, right, I know, oh, this is probably a quadratic form situation. 4, 2, nothing, right? And with quadratic form, we know our strategy is magic X. So I'd say, okay, 48 and negative 14. Two numbers that multiply to give me 48, add to give me negative 14.
-6 and then -8.
Negative 6, negative 8. Now, remember, anytime we're factoring, we're just breaking down a big thing into the multiplication of smaller things. So I'm not solving, I'm just factoring, and this is the multiplication of something, right? Parentheses. I throw in these numbers, -6 and -8, and what goes out front, I have to get right. And when I say I have to get right, I have to imagine, what if I needed to go back? What would I need to be there to be able to get back to x to the 4th? X squared and x squared, right? And if you're always thinking with that mindset where if I wanted to, I could go back, you'll always factor correctly because you can check your work. You can say, yeah, if I followed that, I would get x to the 4th, and then I would be good, right? Okay, now I always ask myself at this point, or at any point in these problems when I feel done, am I done? Can I keep going? And anytime you get one of these, like x squared minus a number, my first thought, I know, probably your first thought is, maybe I have difference of perfect squares, right? And then I say, okay, well, there's a perfect square. There's a difference. What about this number? Not a perfect square. What about this number? Not a perfect square. So if that happens, then you're done. You know that you've checked, you're fully factored, you can't continue. Okay? So that's a quadratic form. Okay? Now, like I said, sometimes you get the GCF and then you'll do quadratic form. So you just have to be ready for either situation. All right, what other type of problem or specific problem do we want to see? Number 9. Okay, so number 9 is a good example of what I was just talking about, right? We're always asking ourselves, which of our situations is this? Sum of cubes, is it quadratic form, is it grouping, right? But sometimes we can't even see that until we check for the very first thing, which is GCF. So what goes into both of these? X, right? So if I pull out the x, divide them both by x, I get x to the 3rd plus 8. Okay, so I've begun to factor this. I've turned it into the multiplication of smaller things, right? But I always ask myself, can I keep going? And what I want to keep going with is the stuff on the inside of the parentheses. That's what I mean when I say, look at that like it's a brand new problem. Like if I just gave you that, what would you think, right? Then I look and I say, oh, x to the 3rd and 8, those are both perfect cubes. So this is a sum of cubes, right? A sum of cubes situation. I got a cube plus a cube. So I rock that mode. I start thinking about it. And I know that that is a situation where you have like a to the 3rd, and you don't have to memorize this. You'll be given this. A to the 3rd plus b to the 3rd equals a plus b. And then a squared minus ab plus b squared. Okay? You don't need to memorize that. In order to use it, though, we do need to know what our a and our b are. All right? So I say, okay, x, and then some people like to do this. You don't have to do this. Rewrite it as x to the 3rd plus 2 to the 3rd, and that gives you your summing to the 3rd, summing to the 3rd, so it gives you that a and that b very clearly, right? Some people also like to do this. A is x, b is 2, right? Okay. All you did was rewrite 8 as 2 to the 3rd, which is the same thing. All right, now I know my A and my B, I just plug them in, right? So this is going to be, don't forget your x, don't lose that x, right? You always need to be able to get back. If I lose the x, I can't. And then I have x plus 2, x squared minus 2x plus 2 squared, which is 4. And because I know the way these things go with sum of cubes, I know that I can't factor that further, right? A magic x would not work there. So this is fully factored. Remember, if I wanted to go back, distribute this, multiply this out, and I should get back to that. Okay? All right, so that was a GCF and then a sum of cubes, right? So we've hit on a few different things. We haven't touched a grouping one yet. Does anybody have a grouping one they want to see? Or just want to see a grouping one? Yeah. Okay. Let's go to number 6. Okay, so number 6. Okay. So first I check, there's no GCF, and then I ask myself, what situation am I in? And remember the quadratic form, I said you would look at the exponents and you'd be like, okay, I got 4, 2, nothing. Well, grouping is another one where you could see it in the exponents. I got what? I got 3, 2, 1, nothing, right? 3, 2, 1, nothing. And I know the 1 is imaginary, right? But it is there. 3, 2, 1, nothing, 4 terms. That's a good sign you have grouping, and that's where you need to go, okay? And it's always good to remember the name grouping because it tells you what to do. Put them into groups. So I make a group here, and I make a group here, okay? Now I GCF each group. This x squared goes into both of these, so I get x squared times x plus 5. And then minus 3 goes into both of those. So minus 3 times x plus 5. Now, a lot of people feel good about this spot, but then they're like, I can't remember what to do next, right? A lot of times when we can't remember what to do next is because we tried to memorize steps, but we didn't try to understand what was happening. Steps don't stick. Understanding the why does stick, because then you just know, okay? So let's talk about it. Remember this thing that I said to do where you say, okay, this, first of all, that's your GCF. That's what you need to pull out. If it's hard to see, you can replace that with a placeholder. So we'll call it z. Z equals x plus 5. Just throw that in instead of x plus 5. I get x squared times z minus 3 times z. Now, if you GCF that, if you pulled something out of both of those, what could you divide those both by? Z, right? So I could, this and this, I could pull a z out. So I GCF the z out front, I'm left with x squared minus 3. Now, we don't want a z in our final answer, so what do you say? We plug back in what z is equal to. What is z equal to? X plus 5. So this goes back in here, and I get x plus 5 times x squared minus 3, right? You don't have to do that every time, put that placeholder in. You can, but if you, it does show the concept, right? We're just GCFing x plus 5 out front. Now, I ask myself if I keep going. I can't because that's just a binomial, and that is not difference of perfect squares. So there you go. You're done. Okay? Questions on that? All right. So I think that's it, unless somebody wants to see difference of perfect squares, because that's the only thing we really didn't hit on. But difference of perfect squares is just a shortcut. Difference and 2 perfect squares, plus minus, square roots, and you're good. All right. Let's go to the notes.